3, the geometry of the universe. The previous chapter demonstrated that any physical theory of the universe must account for the interlinked nature of space and time, and introduce some geometric methods for describing spacetime. Just this chapter puts those ideas together with a crucial insight about the nature of gravity, which led to the development of the general theory of relativity. In this chapter, you will explore the ideas underpinning general relativity as well as some key evidence in support of the theory before moving on to explore two of the most In this chapter, you will explore the ideas underpinning general relativity as well as some key evidence in support of the theory, before moving on to explore two of the most important metrics for understanding and observing the distant universe: the Schwarzschild metric, which describes the space-time surrounding a massive object, and the Robertson-Walker metric, which describes the geometry of our expanding universe. Objectives. Working through this chapter will enable you to explain the equivalence principle and describe its significance for our understanding of gravity, understand Einstein's field equations, and understand and explain, describe Einstein's field equations, and understand and explain the meaning of the terms included in them. Summarize key evidence in support of the theory of general relativity. Describe the behavior of spacetime in the vicinity of a massive object such as a planet or a black hole, and apply the Schwarzschild metric to solve problems in this situation. Understand and explain the form of the Robertson-Walker metric that describes an expanding universe. Define and manipulate three key cosmological parameters linked to this metric: the scale factor, curvature parameter, and Hubble parameter. Figure 3.1, effect of dropping an object in a freely falling lift. Chapter 3, Part 1, Gravity as Geometry, Free Fall and the Equivalence Principle. The extension of the theory of special relativity to encompass the behavior of gravity began with Einstein's realization that for an observer falling freely from a great height, accelerating downwards as a result of a gravitational field, physics behaves as though gravity is switched off. Figure 3.1 shows an observer in a lift falling down an airless lift shaft with no friction, who has let go of an object while falling freely. The downward accelerations of the lift, the observer, and the object will all be the same because a principle called the universality of free fall guarantees that acceleration under gravity is independent of an object's mass composition. This means that the released object will appear to remain stationary to the observer. It will not fall to the floor of the lift because the lift and the object are accelerating by the same amount. If the observer exerts a force on the object, pushing it sideways, they will see it behave according to Newton's law of motion. For example, being displaced horizontally in the direction of the applied force. So the freely falling observer's frame is acting like an inertial frame of reference. Question: if the released object in the freely falling lift appears to float rather than drop to the floor, should the same apply to the person? Answer: if the person was standing on the floor at the time the lift began f- freely falling, then they would remain in the same place relative to the top and bottom of the lift, as shown in figure 3.1. Similarly, if they raised their feet off the ground, they would not drop back to the bottom of the lift. Figure 3.2, effect of dropping an object in a rocket undergoing uniform acceleration. In contrast to the situation shown in Figure 3.1, where the dropped object appeared not to fall from the perspective of the person in the lift, we can consider an observer located in a region where there is no gravitational field. Figure 3.2 shows what would happen if someone dropped an object while in a rocket that is undergoing uniform acceleration and is not subject to gravitational forces. If the uniform acceleration A has the same magnitude as g, the gravitational acceleration on the surface of the Earth, then the observer will see behavior that appears identical to gravity on Earth, namely, the object will appear to fall. The relative motion between the dropped object and the floor of the rocket will be equivalent to that of a released object that falls to the ground on Earth, because their relative accelerations are the same in two situations. Question: how are these two situations equivalent if the rocket in figure 3.2 is accelerating in an upward direction relative to the person inside it, while a person on the surface of the Earth feels a downward gravitational pull? Answer: a person of mass m on the surface of the Earth exerts a force on the Earth's surface of F equals negative mg, and so by Newton's third law, the Earth's surface exerts an opposite force of the same magnitude mg. In figure 3.2, the floor of the accelerating rocket exerts an upward force of F equals ma on the person. So if the magnitudes of A and G are the same, then the effect is equivalent. This agreement between physics in regions of uniform acceleration and in regions under gravity is known as the equivalence principle. This principle has a weak and a strong form. The weak equivalence principle refers specifically to the motion of objects and can be stated as follows. The weak equivalence principle. Within a localized region of spacetime near to a concentration of mass, the motion of objects caused by gravitational effects alone cannot be distinguished by any experiment from the motion of objects within a region of appropriate uniform acceleration. It is important to note the reference to a localized region of space. It is important to note the reference to a localized region of space. Unlike the theory of special relativity, when thinking about general relativity, we need to consider local inertial frames. The location of an observer matters as well as their relative motion. To see why this is the case, consider an observer in a lab on the surface of the Earth who drops two objects separated by a certain horizontal distance. If the objects are falling towards the center of the Earth under gravity, then the direction of the acceleration vectors will be very slightly different, as represented in figure 3.3a. By contrast, for equivalent situations we considered earlier, namely an upward accelerating rocket that is not subject to gravitational field, the direction in which the two objects fall are exactly the same as shown in figure 3.3b. Dashed lines showing the motion of the objects falling under gravity on Earth and be in a rocket with uniform acceleration that is unaffected by gravitational forces. Differences in the motion of the objects become noticeable if the reference frames applied are insufficiently local. Although the difference in the situation of figure 3.3a would be undetectable in a lab-sized region, the slight deviation in the direction of acceleration from the exactly vertical would become measurable with an experiment if the reference frame and the distance between dropped objects spanned a significant angular extent relative to the Earth's center. It is therefore crucial to always define reference frames that cover a region and time that are sufficiently small as to be inertial within the accuracy needed to draw useful conclusions. It is therefore crucial to always define reference frames that cover a region and time interval that are sufficiently small as to be inertial within the accuracy needed to draw useful conclusions. The weak equivalence principle has been very well tested experimentally and is known to be accurate to an uncertainty level of less than 1 part in 10 to the power of 11. The strong form of the equivalent principle states that not just motion, but any physical behavior objects cannot be experimentally distinguished. This is less definitively proven, but any deviations must again be small. Much of the behavior we will consider in the rest of the chapter is a consequence of the weak equivalence principle. Einstein's field equations. The equivalence principle led Einstein to the idea that a metric theory of gravity is possible. Under this model, whose postulates are summarized below, the motion of test particles that are subject to gravity is determined by the form of the metric in a particular location. Instead of being caused by gravitational forces, more specifically in general relativity, test particles, including light, will follow geodesics. What is a geodesic and why might a test particle follow such a path? Answer. Geodesics are the shortest routes between 2 points and so are likely to be the path requiring the least energy. Geodesic paths will differ in flat and curved geometries as discussed in the previous chapter. Postulates of metric theory of gravity. Number 1. The metric the geometric properties of spacetime are described by a metric that encapsulates the influence of gravity on space. The world line of a test particle subject only to gravitational influence, which means not subject to electromagnetic or nuclear forces, is a geodesic of this metric. Number 3. The world line of a light ray or other electromagnetic signal traveling in a vacuum is a null geodesic of this metric. ds squared equals 0. Geodesics in Minkowski flat spacetime are straight lines, which is consistent with the way Newton's first law describes the motion of bodies that are not subject to forces. The influence of gravity must change the form of the geodesics and so cause spacetime to be curved. The general theory of relativity sets out Einstein's theory of how the presence of matter determines the metric of four-dimensional spacetime. More specifically, this theory is encapsulated in Einstein's field equations, which describe in mathematical form the relationship between geometric curvature and the distribution of mass and energy. As noted in the previous chapter, it is beyond the scope of this module to teach the full mathematics of Riemann geometry necessary to derive the field equations. Therefore, we can only introduce them and describe meaning in a qualitative way. This will be sufficient to allow us to use some important solutions to the field equations in order to study cosmology. Einstein's field equation can be set out as in equation 3.1, where g is the gravitational constant and other terms are summarized in table 3.1. Einstein's field equation of general relativity. R mu mu minus half g mu mu r constant equals negative 8 pi gravitational constant g over c to the power of 4 tensor t mu mu. The tensor quantities in equation 3.1 have two indices which cycle through each dimension of spacetime. This means that equation 3.1 describes 2 to the power of 4 equals 16 equations, which need to be solved jointly to find the metric for a particular energy momentum distribution. In practice, only 10 of the equations are independent, so there are usually 10 equations to solve, not 16. Table 3.1. The meaning of terms in Einstein's field equation. R mu mu. Definition. The Ricci curvature. This is a simplified form of the Riemann curvature tensor. G mu mu. The metric tensor. R. The curvature scalar. Further simplification of the Ricci curvature. T mu mu. The energy momentum tensor or stress energy tensor. A set of terms describing the distribution and flow of energy and momentum caused by the presence of matter and radiation. In other descriptions of general relativity, you may sometimes see the left-hand side of the equation 3.1 written in simplified form as a single tensor, g mu mu, known as the Einstein tensor. Exercise 3.1. In Chapter 1, you were introduced to a famous description of the theory of general relativity by John Wheeler. Space tells matter how to move, matter tells space how to curve. Misner, Thorne, and Wheeler, 1973, page 5. Write a short explanation of which elements of the theory of general relativity, as introduced in this chapter, will relate to each half of this description. Solution to exercise 3.1. The second half of the expression matter tells space how to curve is a rough description of Einstein's field equations. The energy momentum tensor is the source of curvature and determines the components of the curvature tensor. The first half of the expression space tells matter how to move refers to what a metric theory of gravity means. The metric space in the colloquial expression determines the geodesics along which, in the absence of external forces, test particles matter must move. The field equations are a very concise way to encapsulate a complete description of how gravity behaves anywhere in the universe for any possible distribution of matter and energy. Solving the field equation is not an easy task, and you will not be asked to do it in the module. For a situation other than the simplest distribution of mass, it is usually necessary to use computational methods rather than doing the algebra by hand. Later in this chapter, you will investigate two of the most important solutions of the field equations: the metric that describes spacetime near a single massive object, e.g., a planet or a star, and the metric that describes the expansion of the universe as a whole. However, we will first briefly discuss how the theory of general relativity can be tested and what evidence exists to convince us we can rely on it for studying cosmology. Evidence for general relativity. A wide range of experiments have been conducted to test the theory of general relativity. To date, the theory has passed all these tests successfully with no evidence of discrepancies. Famous early triumphs for the theory was its ability to predict the precession of the perihelion of Mercury. Midway through the 19th century, it was already known that the orbit of the planet Mercury exhibited some unexplained behavior. The planet's perihelion, the point of the closest approach to the Sun, had been measured to shift position with each successive orbit, as illustrated in Figure 3.4a. Figure 3.4. Two predictions of general relativity. A. The changing orbital shape of Mercury with time, with the perihelion location P advancing with each successive orbit labeled 1, 2, 3. This effect was not explained by Newtonian mechanics, but Einstein demonstrated that it is expected in general relativity, with the predicted angular shift being in very good agreement with what was observed in practice. General relativity also predicts a comparatively large deflection in the path of light traveling from a distant star and passing near to the Sun, as illustrated in Figure 3.4b. B. The deflection of a star's light when the Sun passes near to the star's light path to Earth. Testing this prediction requires making measurements of the positions of stars and recording how these change when the Sun passes very close to their projected locations on the sky. Measuring the resulting deflection is tricky because of the brightness of the Sun, but is possible during a total eclipse. Arthur Eddington carried out a series of such measurements in the early 20th century, which helped to promote Einstein's theory and made international headlines. Figure 3.5. More recently, the predictions of light bending by the Sun have been verified to an accuracy of less than 0.04% using observations of quasars via radio interferometry, a method of measuring radio waves to very high spatial precision. Another famous experiment measured an effect known as gravitational redshift, which is a consequence of relativistic time dilation due to gravity, and is discussed further in section 3.23. The Pound-Rebka experiment of 1960 confirmed that the Earth's gravity causes a detectable redshifting of light, and calculated the magnitude of this to be less than 1% with the general relativity prediction. The Shapiro delay is another important general relativistic effect in which radar signals are delayed when they pass close to a massive object. Modern astronomical observation also provide extensive evidence for general relativity. This includes the gravitational lensing of distant galaxies and quasars, the distortion of their appearance in images due to the path of their light has taken to reach us, and the behavior of neutron stars and black holes, which will be discussed further in the next section. One of the most exciting recent discoveries in astrophysics was the direct detection in 2015 of gravitational waves with an instrument on Earth. General relativity predicts that moving sources of gravitation will emit waves that propagate as time varying distortions in spacetime. Detections of such gravitational waves were made by the Laser Interferometric Gravitational Wave Observatory (LIGO) and the Virgo Interferometer located in the US and Italy respectively, and led to the Nobel Prize in Physics being awarded to Thorne Weiss and Barish in 2017. Gravitational waves had actually been detected more indirectly in the 1970s by monitoring of a binary pulsar system in which two neutron stars are gradually spiraling closer together, with this shrinking orbit caused by the loss of energy via gravitational waves. This earlier discovery also received a Nobel Prize in Physics, which was awarded to Hulse and Taylor in 1993. Figure 3.6 shows results from the two Nobel Prize winning studies mentioned above. Panel A shows the first di- direct detection of gravitational waves. The data are plotted as a quantity called strain, which measures the relative distortion of spacetime in different directions caused by the passage of gravitational waves from distant events, such as mergers of black holes and neutron stars. The experimental data are presented alongside models that are used to interfere the properties of the merging objects. Panel B shows the observation of the decay of the orbit of the binary pulsar system identified by Hulse and Taylor over 17 years. Red dots plot the shift in time of periastron closest approach compared with the orbital chain predicted by general relativity, solid black curves beneath the dots. The lower panel highlights the close alignment between the data and the predicted model. Figure 3.6. The first gravitational wave signals measured independently at the LIGO, Hanford, and Livingston detectors compared with the black hole merger model, red orange lines. Radi- B. Radio monitoring of the orbital decay of the Hulse-Taylor binary pulsar system, red dots plotted against the prediction of general relativity, black curve. The horizontal dashes line shows the expected behavior if no gravitational waves were transporting energy away. The lower panel highlights the close alignment between the data and the prediction model. The lower plot shows the residual difference between the model and the data.